Welcome to your lesson, 3.5 Analysis and Conclusions. At the end of this lesson, you'll be able to describe errors in linear regression, analyze graphs, and determine if line of best fit is the appropriate to predict trends. So let's begin. First, let's review some lines of best fit. Which of the following lines represents the line of best fit for a scatter plot? What's the best line of fit? Is it A? Is it B? Is it C? Or is it D? The answer is C. C is the best line. See, half of the data points are above the line, and half of the data points are below C. In A, no points are above the line, and most of the dots are below it. In B, it doesn't split the data into half. And D, well, all the points are above the line. So C is the best answer to line of best fit. So now let's describe the error in regression for each of the following. So what is the error in this graph? Is the line of best fit appropriate? Well, if you take a look at the points, there are 3 points below the line, and there are 1, 2, 3, 4 points above it, and one that really is basically on the line. 1 point is on the line. So is this the best line of fit for this data? Well, the answer is no. See, this point right here is the outlier. It's so far away. If that point is not considered in the data, the line of best fit would very much look different. It would look something like this. There we go. This would be the line where we don't care about the outlier. Notice there's actually, we're going through 3, 4 different points. There's 1 point above, and there's a little bit of 2 below the line. Well, how about your second graph? What's wrong with this? I mean, it looks like 2 points right there are above the line and 2 points are below it. So that looks pretty good. So what do you think is wrong with this line of best fit? Well, the problem with this one is that we have too few data points. Because we have too few data points, we can't really have a line of best fit. We have to have 10, maybe 15, 20, even more data points to have a trend line. We don't have enough data points to have a trend line. Well, will it be a curve? We're missing some important information right here. What is those dots that are missing? So that's why this is not a really good trend line. It's because we have too few points for it. Our last example is this graph right here. So what do you think is wrong with this graph? Well, what's wrong with this graph is what's wrong is that this line of best fit, even though it kind of goes through half of it, half of the points are above and half of the points are below the line, the points are not located to show a trend. Is this actually a line? Is this increasing line? Is this actually a line that goes down instead? So let's see, well, will this be the correct trend line for the information? Same idea, half of the points above and below. Is this a horizontal line? And maybe it's a vertical line. Well, we don't really know. We can't really tell because there really is no pattern on this data. So because there's no pattern or linear pattern. So now let's talk about errors in analysis. What kind of errors can we have in our analysis of a linear model? So the first error we could have is that the model is based on too few pieces of information, like the example before. The model is based on data that are clusters together. That's another error. There does not appear to have any correlation together, and there are outliers. there are too many outliers, and the data do not appear to be linear. So let's take a look at those examples. Let's illustrate these possible errors. So the first graph illustrates, it looks like a pretty much straight line if you draw a straight line right here. But because there's only 1, 2, 3, 4, 5 points, we don't have enough data to support that this is a linear relationship. So the second graph illustrates kind of a cluster of information. I mean, I don't really see a linear relationship. These points don't really create a line, and they're just clustering away. Okay, so we have cluster, and then it doesn't look like linear. So let's take a look at our third and fourth example. Now, this kind of look like a linear relationship, kind of. Maybe it looks like this. But because there's so many outliers, so many points that are above and below, so far from it, that I think there's just too many outliers for our relationship. Now, the fourth example, I mean, you have these so many dots, but do they really form a line? I don't really see a line forming. I don't see a linear relationship whatsoever. So that's the reason why this would be an error analysis to assume this is a linear relationship. For our fifth example, we have this data point that it really doesn't look like there's a relationship, definitely, but it doesn't really look like there's some type of linear relationship. I mean, if we could trace the relationship, it looks like it's more of a curve. And again, that's not linear. So that would be our error analysis. So this is not linear. The next thing that we have to talk about is cause and effect. So what is cause and effect? Observing a relationship between two variables does not mean that one variable causes a change in the other. Other factors could be involved, or the correlation could be a coincidence. Demonstrating cause and effect conclusively is a challenging task that requires careful analysis and specialized statistical tools. So let's take a look at some examples where I want you to think about three relationships and find out, not really find out, but decide, does one cause the other? So let's read the first example. So a scientific study showed a negative correlation, that means it's going down, between aerobic exercise, that means exercise that requires oxygen, and blood pressure. It claims that the increase in aerobic activity was the cause of decreased blood pressure. What it basically means that if you exercise, does your blood pressure, average blood pressure, decrease? That means does exercise makes you healthier? And the answer is, well, is there a relation? Does one cause the other? Does exercise help you have lower blood pressure? And the answer is yes, it does. Yes, there's a correlation between increased activity to a lower blood pressure. How about the next one? Mila discovers a positive correlation between gasoline prices and the average monthly temperature. She concluded that the temperatures determines the price of gas. So what she's saying is that if the temperature of outside, the weather, increases, does that cause gasoline prices to increase? Well, the temperature causes the gas prices to increase. Well, the answer is no. The temperature has it has no effect. That means it does not cause the gas prices to increase. However, it often does. Just for a little tip of information, one of the most gas prices in Canada happens around September. And the reason for it is because during September time, even though the temperature is not the highest, refineries go through a shutdown phase and they produce less gasoline, and gasoline prices go up. because there is more demand and less supply. Let's take a look at a third question. Since 1950s, the concentration of carbon dioxide in the atmosphere has increased. Crime rates in many countries have also increased over the same period. Does more carbon dioxide in the atmosphere cause people to commit crimes? Does this have cause and effect? Does pollution basically cause more crimes to be committed? And the answer is no. One does not cause the other. And that's cause and effect. Let's take a look at the next slide. Now we're going to perform an analysis on a X and Y scatter plot. So the table shows how wind affects a runner's performance into 100-meter dash. Positive wind speed corresponds to tailwind, and a negative wind speed corresponds to headwinds. The change t in finishing time is different between runner's time when the wind speed is at S and the runner's time is when there is no wind. A little bit tidbit information. If the wind is too strong in run races in the World Championships and Olympics, the runners are not allowed to race. Why? Is because if the wind is too helpful, they could beat world records. And if the wind is hindering their performance, then they will never be able to win world records. Ideally, we want the wind speed to actually be at 0 meters per second. So we have this chart, and let's talk about this data first. So we have wind speed, and this is meters per second. We have -6. That means it's blowing to your chest. -4, -2, 0, there's no wind speed, 2, 4, and 6. And this is the possible change in time on average due to the hindering or helping winds. And we're going to plot this, and we have to kind of decide which one is the X value, which one is the Y value. And because one causes the other, what causes the other? Wind speed causes the change in the finishing time. So the top values right here are going to be your X values, and the corresponding changes in time will be your Y values. So we're going to plot this using Desmos. So we're going to jump into Desmos right now. So now we're in Desmos, and we're going to create a table. In order to create a table, we'll click on the Add button and scroll down to Table, and our X values will be the values that we had in the chart. So we have -6, we press Enter, -4, Enter, and so I'm going to fill this table from the values that we have in the question. Here we go. These are the values from the question, and here is our scatter plot. Now take a look. Does it look like linear? Well, it kind of does. It kind of looks linear. But you know what? It kind of also looks like a curve, and we're going to investigate this. The first thing we're going to do is we're going to draw, you're going to make the Desmos do a linear regression for this, and find the coefficient of correlation. So in order to do that, go to second cell and type in Y1. And Y1 is the table of values for the Y's. And then we go to our keyboard, and then we're going to type in ABC, and then we're going to find for this kind of like approximation symbol. And then we're going to type in M, and then X1 to symbolize the data in your X1 column. And then we're going to type in plus B and see what happens. Close down this. And then there is this linear regression, and then we get our R value of -0.784. And I want you to guys remember this value. I don't think I can copy paste this. There you go. We copy and paste it into our sheet, and we're going to look at the R, the coefficient of correlation, but also we're going to take a look at R squared. And then what we're going to do is like, well, I said that that this is a curve, and we can actually do a regression of a quadratic. Even though you're not expected to learn this in this unit, but it's actually good to see if the correlation of the quadratic coefficient is actually better than the linear one. So we're going to do a regression of the quadratic. So let's go back to Desmos, and we'll do that. So let's do it again. So this time we're going to do y1, and we're going to start the same way. Go to your ABCs, find the approximation symbol, and instead of going mx, we're going to type in ax1, and then we're going to find a square, and we're going to add plus b x1 plus c. This is the general makeup of your quadratic equation or a curve. And now let's take a look at the curve. It looks like this. And take a look at the r squared. Take a look at that. And we're going to copy paste, and we're going to compare it to our linear one. Actually, we just scroll up. Now take a look. What's better? Well, we have r squared 0.9572 or r squared 0.9952. Which one's a better which one coefficient is better? Well, the coefficient for the quadratic is better because it's closer to 1. This value is closer to 1. So this is more of a non-linear equation based on these correlations. I got a little bit ahead of myself, but let's take a look at just this question. Use linear regression to model the relationship, record the slope and the vertical intercept. So right away, just by looking at our regression, we get the slope is equal to negative 0.335357, and the y-intercept, which is b, 0.261429. For all intents and purposes, we're going to round up to 2 decimal points. So our slope will equal 0.34, while y-intercept will equal to 0.26. We could round off. Now, is the line of the best fit appropriate? Explain. So I would say no. No, it is not appropriate because we should have capital letters. No. Because the quadratic coefficient of regression is closer to 1. Okay, hopefully you enjoyed this lesson. Stay tuned and have a great day. Bye-bye.